consistent layout on the local file system of each machine. When people want to use any of these clusters, they just need to specify the configuration folder of the cluster as part of the Hadoop command. This approach helps us to solve some major issues. First, it allows us to continue to scale. Second, we can run Hadoop in different data centers. Third, it provides good isolations. However, as the number of clusters continue to increase, this approach also has its limitations. The first problem is usability. From end user perspective, they need to know about names of different clusters and locations of different data sets. From Hadoop service owner perspective, this means extra burden of support and maintenance. Sure, we can build abstraction and tools for this, and in fact, that's what we have been doing, but this also adds an extra layer of complexity. The second problem is efficiency. Due to static partitioning, spare resource cannot be shared across different clusters, and popular data set will now need to be replicated to more clusters, which creates overhead in storage, network, and I/O. So on one hand, we need to use multiple clusters. On the other, we don't want to have too many of them. Is there any other option as we continue to scale? And that's what HDFS Federation is designed for. And before we talk about federation, let's do a quick overview about HDFS. HDFS is a distributed file system used extensively within Hadoop ecosystem. It supports the traditional hierarchical namespace, including directories and files, just like any other file systems. Architecturally, it consists of name nodes and data nodes. With data node stores the actual data in the form of HDFS blocks. Name node maintains the global namespace and metadata, such as block locations and how blocks maps to files. Name node also supports high availability by running on different machines, with one being active and others being standby. And in this example, we have a data warehouse cluster consisting of one active name node and one standby name node, and a bunch of data nodes reporting to both name nodes. At the API layer, HDFS provides a client-side library based on Hadoop file system interface. When a user runs a Hadoop command, in this case, trying to download a file from HDFS, the client-side library, also known as distributed file system, will transparently resolve the logical namespace to the active name node, get the block location from the name node, and fetch the actual data from the related data nodes. And because name node stores all the namespace and metadata information in memory, name node will become the bottleneck if the namespace and metadata is too big. Federation solved this by statically partitioning the global namespace into individual disjoint namespaces, each of which is managed by a dedicated name node. Each name node also manages the collection of blocks, as known as block pools, corresponding to its namespace. And each data node can choose to store one or more block pools. The same data warehouse cluster, for example, can be partitioned into three namespaces: temp, user, log. Each namespace has its own dedicated active and standby name node, and each data node in the cluster stores data from all three namespaces. Instead of exposing these individual namespaces directly to applications, Federation provides application a single logical global namespace to use, and internally maps directories and files on individual namespace to logical path on the global namespace based on a mount table configuration file. And this is similar to how Linux mount these partitions to logical path on the local file system. This client-side mount table functionality is provided by View File System, which is based on the same Hadoop file system interface. When an application interacts with a federated cluster, they need to specify view fs as the URI scheme. And then the view file system will transparently be loaded into the application process and handle the namespace resolution. Putting things together, when the user runs the same Hadoop command against a federated cluster, because the path starts with /user, view file system will map that logical path to the user namespace and invoke the distributed file system instance of the user namespace. After that, the distributed file system will perform the normal handshake with its name node and related data node, just like the non-federated use case. With federation, now we can combine multiple physical clusters into one logical cluster at the HDFS layer. And at the MapReduce and YARN layer, because the scale limit is higher than HDFS, we can just group those machines together. As a result, we end up with fewer number of larger clusters. And for example, at Twitter, we have between 2 to 4 namespaces per cluster, and most clusters have thousands of nodes each. After running many applications in this setting, we identify some common usage patterns and problems people often run into. The first pattern is per cluster interaction, and the common Hadoop operation fall under this category. For admin operation, because tools like FSCK don't support federated cluster, the individual namespace within a federated cluster also needs to be specified as part of the Hadoop command. And sometimes people want to do file lookup across different clusters, and might end up writing scripts like this. All these examples show that even with federation, usability remains a problem. The second pattern is data replication from one cluster to the other. To support that, Hadoop comes with a tool called DiskCP. DiskCP uses MapReduce to achieve efficient distributed copy and fault tolerance. However, when we run it against federated cluster, we run into some problems. In this example, we have a DiskCP job that specifies the configuration folder of the target cluster. As a result, the DSCP MapReduce job will run on the target cluster and pull data from the source. Now the question is how to specify the source cluster location. Unfortunately, we cannot use source cluster's global namespace because that namespace is only defined in source cluster's mount table file located within its own configuration folder. To work around it, we can directly use the active name node of that specific namespace within the federated cluster, but that will break the abstraction of federation and high availability. Each time there's a name node failover, we have to change the parameter. Alternatively, we can use HFTP protocol in conjunction with server-side redirect. However, HFTP protocol isn't as efficient and reliable as the HDFS protocols. Another related use case is cross-data center synchronous write, where applications need to make sure data is written to all data centers before moving to the next step. Unfortunately, Hadoop doesn't provide native support for this, and it's up to application to implement the solution on its own. And to do it properly, it's not trivial. For example, application need to make sure the result is strongly consistent in case of failure. And for better read performance, local data center should be chosen over remote data center. All these usage patterns suggest that while multiple federated clusters help with isolation and scalability, it is still not easy to use, and features like cross-data center strong consistency remain unavailable. And now I will hand it over to Gara to talk about the solution.
Thank you, Ming. Okay. So my part of the talk consists of two parts. In the first part, I talk about bringing all our file system resources into a single namespace, and in the second part, alludes to the later problem that Ming was talking about, where we need to replicate data synchronously across multiple clusters and read it in fault-tolerant way. So just to reiterate what Ming was alluding to from the infrastructure side, that's what it looked like for, let's say, a new employee at Twitter. So we're dealing with incompatible, 1.x and 2.x clusters at the same time, a mixture of different file system implementations, and they have different characteristics. HFTP wraps HDFS, but it provides only read-only capability, and it's not aware of HDFS, HA initially. We did some work and presented it 2 years ago together with Lihid. And HFTP is used even for copying data between compatible clusters because of the way our config management works. We configure all clusters in isolation from each other because it's much simpler deployment. And so this generated quite a bit of support workload on our support channels. So people would complain that the job fails with a read-only exception because they accidentally used HFTP. They would say, listing files works very well, but the job fails on file not found exceptions for the input directories, things like that. And my favorite one has always been where people accidentally insert a port from a different file system implementation into another URI. And people who are not familiar with the Hadoop ecosystems and do not know that HFTP is read-only, they always ask us, so I heard I need to mix HFTP and HDFS URIs in a single command, but is HFTP for the source or for the destination? So this motivated us to think really hard how to get rid of all these URIs. So here just, again, the logical view of our clusters. In terms of HDFS, each Hadoop 1 cluster consisted of a single namespace, and as Ming mentioned, we had multiple namespaces for the 2.x clusters. And yet, so since we already use VFS, we were able to abstract these clusters from the users as at least within this one logical cluster. So thinking about a little further, you realize, okay, so our 2.x clusters are actually not really a single cluster in the physical sense. It consists of multiple clusters. We have one, it's more of a logical deployment unit. We have one Yarn cluster with a resource manager and node managers, and we have 3 HDFS subclusters representing namespaces, which we glue together with VFS. So if we are able to glue together multiple clusters within a single logical cluster, why don't we why don't we integrate all clusters in the same namespace? So the only issue then we need to resolve is how to make sure that these namespaces do not collide. And the answer is pretty obvious in terms of how we think about deploying clusters. We deploy them with different data centers. So the root component will be the /DC, and each cluster has a logical name, like cluster A. And again, we have even more challenges on the infrastructure side because more different companies join Twitter after acquisitions. They often come from AWS, so they may have a part of their data on S3. So we can integrate that, and similarly, we can even integrate the local home and temp directories for the user. And I will explain why it's useful. So now the question is, how do we get there? We can, of course, create this ginormous global config, but it's not why is it defeats the purpose of dividing the cluster in logical units to begin with, to make it more manageable? We can try to factor out common keys that I needed for multiple deployments and put them in a special file and import them in all other configurations. So that's not very easy in our current config management system, and also the way you import keys within XML files is thexinclude, and we hit a bunch of bugs with that. And so I think it's not a very often used feature. So what we're arriving at as a solution that sometimes it's much easier to change software than configuration. While it's a challenge, but it also presents a nice opportunity how we can integrate it in a pretty transparent way. If you saw our presentation 2 years ago, you already saw that we have an interesting solution where we have a wrapper VueFS implementation, what's called Twitter VueFS, that treats both HDFS and VueFS URIs the same way. And this is because when we were migrating to Hadoop 1, from Hadoop 1 to Hadoop 2, it was very difficult to change all millions, Hadoop applications at Twitter to use the proper URIs. And this wrapper is our default file system implementation. So this is kind of the thing that boots first, so we can be very creative in what we do there. As Ming explained, all configurations are stored on the gateway node under the same subdirectory etc Hadoop, and then individual directory for all clusters. So we can come up with any glob we need to merge configurations together. So we generate a globally meaningful configuration on the fly. And this configuration, we need to make sure that it's used as a basis for further job submissions, work in scalding REPL, for example. And since all the dynamically generated keys are included in the job submission in job.xml, we actually submitting the same view to the cluster, and we don't need to do any work on the cluster side. So let's take a look what's involved in generating such a global config. While we maintain special mount table XML files for VueFS, logically they are X-included, physically they are X-included for core sites. So basically we need to process all core sites and to create a global namespace, and then we need to process HDFS site to get all the necessary HDFS client information to access all HA nodes across Twitter. So then we do this manipulation with a prepending data center cluster to original path. We preserve the original path as well for such that we can access the files in the usual way as we did before. And then, as I mentioned, we include local mounts. So let's see so let's see in more detail how we go about constructing the mount table. So you have the original link that with the prefix fs fufs mount table. And the link, it's followed by the entry called actually mount table ID. In this case, it's C1-DC2. So it means cluster 1 and data center 2. And then the actual link name was /user, and the URI it points to. This URI is typically HDFS HA name service. So then we just check whether it's Hadoop 2 or Hadoop 1. In the Hadoop 1 case, we swap the scheme to FTP transparently. So what it gives us already at this stage, that if we list /DC star, we get all clusters available at Twitter. That works because this is a client-side implementation of VueFS. We don't need to talk to any HDFS clusters yet. So the HDFS configuration doesn't matter here yet. Then we add local mounts under /local. So why I like this is because people who come from non-Hadoop, they are not aware of this special treatment for the local file system, and they don't like that you need to remember syntactic sugar commands for copy from local, copy to local, and so on, which is, of course, conveniently also abbreviated put and get, but they can learn it in the second week at Twitter. But at least normal commands work right away. So you can just use -cp. So then we are coming to the point where we have the namespace defined. Now we need to make sure that the HDFS works. So the key configuration key for HDFS HA is DFS name services that we need to merge from all the configurations we're dealing with. So we just build a ginormous comma-separated list and stick into the global config for DFS name services. HDFS site itself already obviously supports keys per name services, so we can just copy them over. They have the right config suffixes. As the most important keys that we're dealing here with are failover provider configuration and the node RPC addresses. Actually, there is not much more behind that if you don't need to tune things like RPC, things like that. Right. So when we put it all together, so we already have a working, global namespace with HDFS, local file system, and potential other file systems. So what we were not able to do before, and now it's very easy, we can simply, for example, display my quota usage across all data centers as a very simple glob. We can run FSCK without thinking what namespace ID it had for this specific path. Most DCPs go from a production cluster to the default cluster, so I don't need to specify any configuration directory. Just simply say DCP from DC1 something production to my local system ad hoc path on the ad hoc cluster. And what the data scientists often like, that they don't even need to DCP data back and forth between clusters. So if it's small enough, they can pull it into a REPL simply by directly specifying the path. So to a reassurance that what we were doing was right came pretty fast, based on the feedback we received both internally and externally, or publicly, let's say. And by the way, the reason why I call this thing initial implementation #DCP is because it was DCP with less typing with less characters. I don't know whether it was a good idea after all, but I cannot change it anymore. So the second part deals with the second case where we run a lot of microservices, as you know, at Twitter. They run typically on Mesos in the same cluster, in the same data center as Hadoop clusters. And they often store their configuration or even machine learning models that are produced by some pipelines in Hadoop, and they need to boot a lot of instances on Mesos using these files. So they use, basically the pattern is that in every data center, you have a cluster in the same role. Let's call it cluster CL. And so we have this cluster CL in DC1 and DC2. And so all what they want to achieve is that when one of the clusters is in Hadoop clusters is unavailable, they can read from the nearest HDFS or most recent replica among all of them, just like Ming was describing before. So we want to solve this problem once and for all and don't want every service to write the same logic again and again. So far in ViewFS, we have direct correspondence between one-to-one mapping between virtual inode, virtual path, and a physical URI. But we can do better. We can generalize it. We can store multiple URIs in the same inode. And so then all operations that appear from the client-side perspective going against one path actually operates on multiple clusters at the same time. It could be also just on parallel directories, but the most obvious use case is when you read or write from the same cluster role in different data centers. Let's say we're implementing the policy of the reading from the nearest cluster. So what we can do, we can use the network topology to sort the client node together with the target URI authorities. The same way HDFS client would do with the client node and data node addresses. The only challenge here is that our authorities are not real host names. Those are just logical name service IDs. But since our SREs were already smart enough to deploy and put the data center into the name service ID, all we had to do is to modify the topology script to interpret it accordingly. So it spits out the data center name service network topologies so it can be sorted correctly. And we care only about data center locality, so we just want to avoid reading from a remote data center if the nearest data center is available. So this kind of policy doesn't need to interact with with the URIs up front, so it can be completely implemented or executed on the client side. Of course, if you want to do most recent reads, then you need to check the path on each destination cluster and pick one with the biggest modification time. It's obviously much more expensive, but if the use case requires it, we'll have to pay this price. An additional option is, so when you do these checks of the file status, you might encounter that so the write didn't propagate to one of the clusters, or one of them went, so the data can be either completely missing or stale. And we offer an option where during the read, you actually transparently repair this missing data or stale data. So our read can actually turn into a write. So let's, so this, the part about read was already useful even without implementing write. It's just because how our systems propagate files to different HDFS clusters already. But we can also implement a write, and we did, for such a multi-URI inode. So what we want to do is that the client, let's say it's a client on DC1, writes to a special file. So it uses one path, one logical path. It's the mount, it's the link name, nflies cluster something, and then the usual path. But what it boils down to that we write to two data centers transparently. And the way we do it by intercepting the create and write calls, such that on write, we get a special output stream that will write first to the first cluster, then to the second cluster. And usually it does this to the temporary names, such that this path will not be accidentally included, for example, as an input of a MapReduce job until this transaction concludes. And the transaction concludes on close. So on close, we do rename, and then we obtain the green, I hope it's user Cecily file text, on both clusters. So this shortens sort of the window of vulnerability because writes can take much longer. And so we prevent that by doing this, that we shrink the likelihood that the client crashes during writes in an inconsistent state. So obviously there are some challenges with such a client-driven replication. So we don't use pipelining like in HDFS. So we basically stress the client-side NIC. And normally it's a problem, but not in this use case. We're not talking about big data use case. It's about files that up to a few gigabytes big. Then, okay, obviously, if client dies, like we might be left with some temporary files on one of the destinations or all of them. So who is going to clean up? Because when the client dies, the state is gone. This is pretty easy at Twitter because we already have a retention manager, and we can set up a policy to pretty aggressively clean up these files. But if they don't present much of a load, it actually doesn't even matter. Okay, so when minimum replication is reached, right, the client write already returns, but there are still some destinations that haven't been updated. So how can this be recovered from? Well, one thing is that, as we mentioned, we support read repair. So if you happen to have a client that attempts to read from a destination because it's the nearest one, and it detects, okay, the cluster is now available, but the file is missing, so it can just copy things over from the next nearest replica. And we can also employ our other internal tools to synchronize different file directories. Okay, so I'm close to concluding our talk. So we published this material on our Twitter blog, development blog, and it drew some attention from the community. So I believe some organizations implement approaches close to ours, especially related to creating a single namespace transparently in multi-cluster setups. But if you followed, the work of presented already at this Hadoop Summit, more specifically from Microsoft, so there's definitely more efforts to create transparent federations, and that are much more involved. For example, they will also do load balancing between the namespaces that we don't do, so that avoids static partitioning and long-term imbalances. But so obviously what we did is much, it's less profound, but it was much faster to implement, and we ran with it already for a significant time. So in the summary, we presented to you our multi-DC cases, Twitter, and our approach to simplify this complicated infrastructure using a single namespace generated on the fly. And we have our own pragmatic solution to cross-DC replication. So this work, of course, wasn't done in isolation. So we are thinking to other members of the Twitter Hadoop team, in particular, Lahid and Laurent. So yeah, thank you very much, and I hope there are some questions. It's a good question. So we basically do whatever is configured by default. Yeah, so you end up end up having local 3 replicas just due to HDFS. But you are right. We might be interested in decreasing the replication factor in such a setup where we replicate to different clusters, especially in different data centers. It's just a trade-off. It's a tunable thing.
So you mentioned that for the right replications, when it happens on the client, it's not necessarily like a
So, yeah. So as I said, the key use case is interactive microservices, and that bootstrapping either based on some, if they run some prediction, they just need to consume a model. The models are not that big; they are just 1 to 5 gigabyte big. And the other obvious use case are like configuration and translation bundles. It's only 100 megabyte kind of range. I mean, maybe you want to take some. Okay. Yeah.
A typical deployment, each data center has 3 namespaces. How do you partition the namespace within the single data center?
Oh,
The
yeah.
question
I
is-
guess I need to repeat the question.
Yeah, so to repeat the question is, how do you partition data within a federated cluster? Is it
Typically, you have
3
3.
namespaces? Yes. Okay. So the example you see in this on the slide is we have temp namespace, we have a shared namespace, and then we have a user namespace. The temp namespace usually are short-lived data that could include like job staging data as well as YARN logs. The share or the log namespace are usually for common data set, lots of job want to consume. The user namespace, really depends on the users. People can read the data from the share log namespace and then write the output, whatever machine learning they come up right to their own user namespace. So there are different characteristics, and overall we feel that these things work for our workload, and we don't really need to balance as much as we need.
Did you mention temp?
Yeah, I mentioned temp.
Yeah.
Yeah. Okay.
Temp.
All right. Thanks, everyone.
Thank you very much.